So today I'm here talking about self-organized critical behavior and marginality Ising classes. The title of my talk is shared with a recent preprint, whose latest version went up on archive yesterday. So if you find some of these things interesting, I urge you to go back and check out this archive article for more details. So the main message that I want to convey is threefold in nature. First of all, I want to talk about these non-equilibrium quenches which happen in a long-range 1D power law Ising spin glass, and show how the nature of the final state attained by these quenches is determined by the nature of the initial state. So initially equilibrated at some temperature T, and if that temperature happens to be greater than the equilibrium transition temperature, then the final state also has paramagnetic properties. So in particular, it has a trivial Parisi overlap, and if the initial temperature is less than the equilibrium transition temperature, the form of the state resembles, it has a non-trivial Parisi overlap in the final state as well. The second point that I want to convey across is that there is marginality, marginal stability of these final states if this parameter sigma, which governs this power law decay, is in the mean field regime, and if, on the other hand, if it is chosen from outside the mean field regime, then the distribution of local fields is consistent with non-marginal behavior. So I'll explain what these mean as I go along. And the third point I want to talk about is that of self-organized criticality, and view it from a static picture, and in particular with the help of a spin glass susceptibility, which is computed in the final state. And so once again, if you're within the mean field regime, so it turns out that the spin glass susceptibility diverges logarithmically with the number of spins n, whereas if you're in the non-mean field regime, there is no divergence in spin glass susceptibility, indicating that the quenched state is not critical. Okay, so the model that we consider is the Kotliar-Anderson-Stein model, which is a long-range 1D model where interactions decay with distance as a power law. So the distance is chosen to be the geometric chord distance, which gives you some calculational advantage. You put all the spins on a circle and then draw chords between I and j, and then the distance is that of the chord. And so there is this exponent sigma sitting here with the parameter sigma, so which I already talked about. And there is a normalization constant which is written as C here, and which is set in such a way that the mean field transition temperature is going to be unity, and of course epsilon ij is where the glassiness is. It's a Gaussian random variable of mean 0 and variance unity. So this model has a lot of history to it. I mean, it goes back to Dyson, when he studied with the ferromagnetic version of it, and later on it has been also subjected to a lot of study in the glass variant of it as well. So it is known that there is a phase transition if sigma is less than 1. So if sigma is greater than 1, you get into the short range universality class, and the spin glass transition temperature is just 0. And if sigma equal to 0, that goes to the Sherrington-Kirkpatrick model, which is where most analytical results are available. It's only in that regime. And so, but there is this whole region between 0 and half, which is what's called the infinite range regime. And so it has been argued in recent times that not only is this sort of qualitatively like the SK model, but in fact, it should be exactly like the SK model. So there is a recent work by Mori, Akashi Mori, and others, I guess, which almost enjoys theorem status, which suggests that, in fact, many quantitative aspects in this entire region will be just identical to that of the SK model. And so there is this region between half and 1, which lies in the a long-range universality class, which will also have a finite temperature phase equilibrium phase transition. So today, what I want to talk about is quenches in this kind of a model. And so the protocol that I use is the following. So we start with some initial state. So which if the spins are chosen to be completely random, so then you say that you're at infinite temperature, but you could also start and equilibrate your system at some temperature and then do the quench. So the quench is simply scanning sequentially along your spin space. You go to spin 1, find the local field that the spin experiences and simply align the spin to the local field. And then go to spin 2, find the local field, align it to the field and so on, and carry this through all the spins that constitutes one sweep. And so this is in this process, you're constantly going down in energy. And so it's a monotonically energy decreasing process. And eventually you'll reach a point where it's not possible to change any spin. So then you have hit a metastable state, right? So depending upon the initial state, you will reach a different deterministic sort of final state. And so you have a lot of these final states because that's where the glassiness comes in. So a lot of metastable minima, and a study of the overlap between these minima is insightful. In particular, by studying the distribution of these overlaps, one can see if there is a glassy features are there in them or not. And so there is this theorem by Newman and Stein from 1999, which says that if you start with a random initial state and quench it down by a process similar to this, or I mean, you can also have other protocols of quenching. So the theorem says that the final state should necessarily be trivial. So you cannot get these replica symmetry breaking type of final states if your initial state is completely random. So our finding is that, so in fact, if you start from any state with a temperature T greater than the transition temperature, you'll still get a trivial state. It's not just, so this is a statement about infinite temperature, and it is a theorem. Ours is numerical work, but it's plausible that for any temperature T greater than Tc, in fact, you'll get only a trivial final state. However, if your initial temperature is less than Tc, a non-trivial P of Q is found. And so here I have results for this claim, to back this claim. So I have on the left-hand side data for the Sherrington-Kirkpatrick model in the center for sigma equal to 0.75 drawn from the long-range universality class, and sigma equal to 1.5, which is in the short-range universality class. So here you see that the transition temperature is at 1. So for temperatures, if the initial temperature is greater than 1, so the final state P of Q has a form which is just a simple delta peak in the thermodynamic. It's going to go to that in the thermodynamic limit. Whereas for temperatures even slightly lower than 1, you already start seeing these sort of non-trivial features coming in here. And that is also true for sigma equal to 0.75. The transition temperature is 0.62. This is known from earlier studies. And so indeed, when you come to the blue curve and orange, yellow and orange curves, these are in the non-trivial phase. And for sigma equal to 1.5, so there is no transition temperature. Therefore, no matter how small the initial temperature is, you would always end up getting just a trivial overlap distribution for the final state. So now I want to go to the second message that I want to describe. So this is about marginality and the distribution of local fields. So one can study also the distribution of the final the fields in the final state. So the fields, the magnitude of the field is on the ith site is defined like here. So you collect all the fields on all these sites and then find their distribution. And so it has been, so the old work of Palmer and Pond and others argued and numerically showed that this distribution, if so they looked at just the SK model. So we use these Mori ideas to suggest that if sigma is less than a half, this distribution should be like the SK model, and it goes linearly for very small fields. Whereas if your sigma is greater than half, and if one expects marginality. Marginality is the statement that systems are are stable, but only barely so. So somehow the system in various dynamics tends to go to a state which is just on the brink of stability. And so there was recent work by Marcus Miller and Matthew Viard, which has posited this form. So if we assume this form, we have certain arguments to make. So first of all, I want to show that indeed this linear behavior is something that our numerics does reproduce. This has been seen in other studies as well. So P of H goes linearly with H. There is a finite intercept at H equal to 0. This is a finite size effect. And so if you were to make a careful study of P of 0 as a function of n, you'll see that it falls off as 1 over square root n. And in the thermodynamic limit, there is no intercept at 0. And the slope is also something that we can expect, which I'm going to talk about in a moment. Okay, so there is this argument which is in Palmer and Pond's paper, and so they say that it was, Phil Anderson who came up with these ideas, or they probably extended and so on. And so we also go back to this argument and build on it. So think of the lowest n local fields, or arrange them in increasing order. And so suppose when one were to flip all of these, the spins which have these lowest fields. So with a little bit of work, one can show that the change in energy is given by this expression. So the summation here runs only on those n spins that you have flipped. And so then in addition to this, oh wow. Okay, so I have a lot to say. Okay, so there are these expressions that you can analytically write down for change in energy. And so you also exploit this form that you have posited in the sigma less than half and sigma greater than half. And then if you use this, you can write down this expression. And so the statement about marginality is that this delta E is exactly 0. So if you do this, then you get H equal to this quantity. And in this case, you get another value. So, and we see that for if sigma is less than or equal to 0.5, the slope is given exactly by this prediction of marginality from Anderson-like argument. Whereas if sigma is greater than 0.5, and then you have this green line, which would be the expected value, but the numeric shows that it is far away from which, indicating that the system is more than just marginal. It is completely stable in this region, and there is an alternative way to also arrive at this kind of system. There's more evidence for this just by studying the size dependence of the lowest value of the field. And then the third statement I'll just quickly rush through is that spin glass susceptibility, which is defined like here, it's the standard spin glass susceptibility, except that this average with angular brackets is now done over the metastable states, and then there is an average over disorder, can be useful to make a statement about self-organized criticality. So we see that if sigma is less than or equal to 0.5, all these various data points actually basically sit right on top of each other, and it diverges logarithmically, whereas if sigma is greater than 0.5, all this data is for greater than 0.5. These are linear curves which indicate that they will have a finite value. So these things saturate, indicating that there is no divergence of spin glass susceptibility. These are some more details which I'm going to skip. There are some statements you can also make based on the value that the energy takes. So the conclusions from our work is that in the KAS model, there is a connection between self-organized critical behavior and marginality. Self-organized critical behavior can be studied with the help of spin glass susceptibility without recourse to dynamical quantities like avalanches and distribution of avalanches, which is how they're often studied. And so the regime where marginality is obtained is also the regime where there is self-organized criticality. And so these are states which are at some kind of a critical energy when sigma is less than or equal to half. And it is striking that the transition which is self-organized can be identified. It is a transition where the states which have this kind of non-trivial replica symmetry breaking type of final states. And it will be interesting to see if there are all kinds of systems which people claim are marginal, if there is some underlying self-organized criticality in these models as well. Thank you.
One question while the next speaker gets ready.
So is there any relationship between this overlap distribution function that you get at equilibrium and the one that you get after you quench and look at the metastable states?
Correct. That's correct. So if you start with your a state with non-trivial overlap distribution, the quench state also will have similar overlap.
So these two are, I mean, one can relate the one that you get at thermodynamic equilibrium to the one that you get after you do the quench. Okay, that's very interesting.
Yes. And so in fact, this could be useful as a way to capture the transition temperature itself.
Right.
It's kind of a technique which has not been exploited so far.
Okay.
Yes. Right. Right.
And the value close to 0 goes down.
Right.
So do you see similar things for with the larger system size?
Okay, so that is that's about whether there is replica symmetry breaking or
Yeah, itself.
right.
That's
so
the problem with
we
the
have
replica
looked at
symmetry
very
versus
small
droplet.
system size, so we don't have any statements to make on that.
Okay.
Yeah, so that's why I just said trivial, non-trivial.
Okay, let's thank the speaker.